Hey everybody, we're back. My dog really likes to sleep there. Okay, so what we're looking at now is a sine wave with the 5 points that I'm really interested in on the sine wave. The middle, the peak, the middle, the valley, and the middle. Now this is what I call, the middle again. Now this is what I call the parent function, okay? Parent function is the simplest possible version of the function. In a sine wave, that means the one that's taken straight from the unit circle. One where the period of the sine wave perfectly corresponds to 2 pi radians, one walk around the circle. One that never goes more than one above the x-axis or one below the x-axis, because that's as high and as low as the unit circle can go. Okay? So this is the parent function. It's the simplest possible version of it. But you've seen parent functions before. You've seen parent functions like y equals x squared. But that wasn't the only parabola you graphed. You moved the parabolas around a lot. Okay? So when you did that with any function, what you were really doing, whether you knew it or not, was you were dealing with the difference between the simplest version of a function, okay, that's a parent function there, y equals f of x, and the version of the function that had transformations and translations applied to it, that you might not have learned those words before. So let's slow this part down a little bit. So when you start mucking with a function, changing things around, you get these values that I'm going to include, like a and b, and h and k. And these values all have these really specific jobs. Where have you seen this before? Well, if you remember moving absolute value functions or parabolas around on a xy coordinate graph, if you remember vertex form of a parabola, might have been the first version of this you saw back in Algebra 1 or Algebra 2. If you don't remember it too well, don't worry, I'll go back over the details. So what I've done is I've inserted a and b as things you can multiply, one outside the function, one inside the function, and h and k, things you can subtract and add, one inside the function, one outside the function. Now, let's see what these things actually do. A here, okay, this in any function is what's known as a vertical stretch, okay? It's a vertical stretch. Stretches the function up and down like taffy. We'll see that in action in a minute. Now, in any function, it's a vertical stretch. Put this in a parabola, put it in an absolute value function, makes it taller and less wide, okay? It gets a special name only for sine and cosine functions where it is an amplitude, okay? It's a vertical stretch on any function you can imagine. It's an amplitude on sine and cosine. I won't take off points if you call it a vertical stretch, but you should know the word amplitude as well. Now, another thing we threw in here to be multiplied is this letter b. And this letter b is, got to be consistent with my color coding here, this letter b is a horizontal compression, okay? Now, this horizontal compression, okay, is something that squeezes a function horizontally. Actually, I think I just repeated myself. I don't think I added anything valuable there. What it does is, well, we'll see what it does in a minute on a graph, how it shrinks and compresses sine waves and cosine waves. And it doesn't get a special name, but it gets 2 formulas that we'll talk about in more detail tomorrow. But for now, I just want to preview these a little bit. I mentioned the period last time. Well, the period of your parent function, your simplest sine wave, is 2 pi. It's 2 pi radians is once around a circle. Well, the period of any modified sine wave that you run into is 2 pi divided by this coefficient. So if you see a variable here, use a constant, a number, in front of your x value in your sine and cosine waves, if you want to know the new period of that modified function, and again, don't worry if you're not getting this now, we'll do examples of this tomorrow, it's 2 pi divided by b. if you know the period of your sine and cosine wave and you want to know what coefficient goes there, well, b, that coefficient, will always be 2 pi divided by your period. And tomorrow we'll be meeting synchronously, so then I will be happy to go over exactly how this works, show the algebra on that one. So again, A is a vertical stretch, makes your functions taller as it gets bigger. B is a horizontal compression. It squeezes your function as it gets bigger. I'll show you that in Desmos in a minute. You'll see what I mean. Now these two, they change the shape. Okay, so they get a special name. These are transformations, and they are what are called non-rigid. Okay, non-rigid. They don't maintain the shape. They change what you're looking at. These other two, H and K, these are different. H is what I call a counterintuitive left-right motion. So if you put a number in here, in parentheses, was snuggled up right with your variable, okay, and you're adding or subtracting it, that will move your shape, your graph, any graph you're looking at, left or right. So it'll move your sine wave, it'll slide it down that horizontal axis, or back the other way. Now the reason why I call it counterintuitive, and it's always put in here with a minus sign, is because it works backwards on how you think. We've had you staring at these number lines since elementary school, and positive has always been to the right, negative has always been to the left. Okay, well, if you have this h value inside your function, snuggled up with your variable in there, if it's negative, it moves to the right. Not the way you think, the opposite of what we've been telling you for years. And if it's positive in there, if it's plus a number, it moves to the left. So that's why I call it a counterintuitive left-right switch. And its special name just for sines and cosines is the phase shift. Okay? Now, lastly, we have this K on the outside, and I call this my intuitive up-down constant. Okay? Intuitive because when it's positive, the function goes up. And when it's negative, the function goes down. It's in line with what we've been teaching you. Positive is up, negative is down. So this is my intuitive up-down value. Okay? And its special name, again, just for sines and cosines, is the sinusoidal axis. Okay, it's that middle line, that x-axis on the parent function moves up and down with a sine wave. This is really hard to picture. So what I'm going to do is I'm going to give you a PDF of this. It'll be posted with the work, and I'm going to demonstrate what these do in just a minute. Now, last thing I wanted to mention. These H and K values, my counterintuitive left-right, my intuitive up-down, these are called translations, and they are rigid. They do not change the shape of our values, of our original graph. Okay, if all you play with is H and K, the period will still be 2 pi. Your graph will only go one up and one down from that middle line. Just that middle line might be somewhere else. That 2 pi might start at 0. So I'm going to go and hide myself here for a minute, a little bit, so you can see this, and you can see my graph of a sine wave here, where I've got these folders labeled transformations and translations. So let's start with the translations, my H and K value. Now I've already set this up to take care of the counterintuitive part for you. So when we do some examples tomorrow, you'll see you'll have to switch. You know, if there's a minus H value in here, you'll have to make it a plus value yourself. But I've done that for you a little bit so that you can see H moves the sine wave left and right. Now, see all these decimals I'm getting on these 5 points I care about? That's because, remember, this x-axis is in radians. Radians are multiples of pi. Pi over 2, pi, 2 pi, okay? So if you want to move your graph nicely and neatly, you have to move it in increments of pi. Okay, so if you do that, then your sine wave continues to hit the x-axis at these points that are fairly easy to graph, these multiples of pi. In real life, though, that doesn't always happen, so sometimes you're just stuck with ugly decimals that you can't really do anything about. But don't worry, if you have to deal with that, I will let you do so with technology. If you have to do it by hand, I'll make sure you only move it multiples of pi. Now k, that's my intuitive up-down. K gets bigger, graph moves up. K gets lower, that graph moves down. You can mix and match these. You can move it left, right, up, down, h and k, but they don't change the shape. Notice the shape is exactly the same. Set these back to 0 to get my parent function. Now, let me look at the transformations, a and b. Remember, a is my vertical stretch, okay? So if a goes to 2, my sine wave gets twice as big. If a goes to 3, my sine wave goes 3 units above and 3 units below my middle axis, my x-axis here, okay? And we can mix and match these. 3 units above and 3 units below the x-axis, well, if I change k, then this amplitude of 3 is suddenly 3 units above this middle line, which is the line y equals 3, and 3 units below this new sinusoidal axis of mine. Remember that fancy word? So if I tell you the sinusoidal axis is 3, and the amplitude is 3, you should picture a sine wave that starts at 3 instead of starting at 0, goes up to a peak of 3, back to a middle of, up to a peak of 6, back to a middle value of 3, down to a peak of 0, and back up to a middle value of 3. A, the amplitude, it can be negative. See that? We can go down here. If it's negative, what we do is we wind up flipping our sine wave around our sinusoidal axis. B is my horizontal compression. As B gets bigger, my sine wave suddenly finishes its business in half the space. A colleague of mine used to call B a fast forward sort of option. So see what happens here? When B is 1, let's move this back to our parent function actually. Let's just look at our regular sine wave. When B is 1, our sine wave takes from 0 to 2 pi to finish its business. If B is 2, our sine wave suddenly can finish the same up, middle, down, middle motion in half the time, or half the distance. By the time you get to pi, you're done. Okay? If B is between 0 and 1, it actually makes it longer, stretches out the sine wave. Okay, that horizontal compression, when B is less than 1, becomes a horizontal expansion. And what we now get is, in order to get through our cycle of middle, up, middle, down, middle, now it goes out to 4 pi. It takes twice as long to do it. Take that back to the parent function there. I'm going to let you have a modified version of this Desmos graph as an activity, where you'll be able to manipulate that, and you'll be able to use this on the homework tonight. Okay, so I will post that. And everything I've just told you about A, B, H, and K, remember my original statement, it's true of any function, which means it's also true of cosine waves. If for whatever reason the parent function of a cosine wave is not what you want to use to model your data, well then you can stretch it, and you can flip it over so it looks more like a Liberty Bell, and you can compress it so that it finishes its, well, in the case of this upside down cosine wave, it's bottom, middle, up, middle, bottom motion, when it gets to pi instead of 2 pi. And you can take your cosine wave, let's go back to the parent function, and you can move it left to right, and you can move it up or down. And again, you can mix and match these things. There's no reason why you can't have a cosine wave that is shifted to the right, up 1, finishes its business in half the time, and let's change this here, stretches only half is up and down. I'll fix this so it shows the entire cosine wave before I post this for you to use. Okay, so that should get you started with able to play around with, let's get my parent function back here. This should get you started with able to play around with the homework tonight. Silly made something disappear here. There it goes. Okay, didn't mean to do that. And you will have access to this to do so. The homework is on IXL, so you'll be manipulating these in another virtual environment. I will also make sure that this slide is available to you. And post your questions in the blog forum. Extra participation credit if if you guys answer each other's questions before I have to. And I will see you tomorrow synchronously to take questions in person and to start talking about how to model this data. All right, thank you, and I'll see you soon.